Okay, good evening once again. So today we are considering fundamentals of machine learning. I'm going to follow this outline. We're going to look at attempt some definitions of machine learning, the types, the key components, supervised machine learning, the applications, challenges, the tools and libraries in Python and R. Then we are going to see mainly the supervised aspect, regression versus classification. I think that's where we will stop before we continue. Now, let me ask you, think for a moment, what is machine learning? Try to think of a definition in your mind. So what is machine learning? When you talk of machine learning, how can you best describe it in a simple way? So my attempt today is to make it as simple as possible, but not simpler than what already exists. According to Albert Einstein, this is one of my most popular quotes. Make everything simple, but not simpler. So in a nutshell, machine learning is simply a subset of artificial intelligence. When you talk of artificial intelligence, it's not anything other than some components within it. And machine learning is a major component of artificial intelligence, the popular artificial intelligence that we all shout about. So it is a major component, subset of artificial intelligence that empowers systems, computers, to learn, make predictions, or even decisions from data without being programmed. What that entails is that there are some ready-made algorithms that are already existing, highly data-driven, that you don't need to program them. Again, you don't need to be afraid. You don't need to program them initially. They are there. I'm going to tell you about them. You just need to apply your data, and then those algorithms will make predictions for you. And then what remains is for you to begin to do some iterations with those algorithms now to identify the best pattern in your data and make predictions. And so, having said that, you'll discover that machine learning is highly data-driven. In fact, it works with vast amounts of data. In fact, it drives so many aspects of our work today. And in healthcare, there's no how you can run away from machine learning. You need some knowledge of machine learning because you might need to recognize relationship between your data, you may need to diagnose some diseases using some automated systems, and so many other uses. You may need to detect some patterns. You may need to cluster some variables. You may need to identify some images. Machine learning is what is behind all of this. Either you want to classify some new information, you want to make predictions, you want to take some actions on your data based on on unseen data based on the data you already have, machine learning is what comes to play. So it has gained so much popularity in various fields, including medicine. As you can see, we have a lot of uses in so many fields. In fact, it's almost as if you can't, there's no hardly any aspect of study today that machine learning has not entered into. So you have to do yourself good by learning about machine learning. In fact, if you are conducting a study and you apply machine learning, they look at you twice. So, oh, it's like this person is modern. This person knows what he or she is doing. So you need to really, really be aware of the impact, recent impact of machine learning in our day-to-day activity. So I'm going to tell you, without much ado, the types of machine learning. Putting it very, very simply, what are the types of machine learning that we have? Uh, please take note as we go on. The types of machine learning will depend on the types of data that you are working with or working on. Please take note of that again. The type of machine learning will depend on the type of data that you are working on. Take note, there's going to be a quiz after this as part of your assessment. So, machine learning, I've told you before, is highly data-driven. It's based on some prepared algorithms that works on data without being explicitly programmed. You don't need to be afraid. It's not rocket science. It's something that you also can do. Everybody can use machine learning, right? So you must uh, uh, be ready, open your mind to the types, to machine learning, to the types of, or you must be able to identify the type of machine learning you want to, although it's very broad, then we need to take it gradually. So the first one I'm going to talk to you about is what is called supervised machine learning. Supervised machine learning. So what does this entail? It is a type of machine learning that makes use of labeled data. No, that's what I said. I said the type of machine learning you will use depends on the type of data you have at hand. Don't forget, everything is data-driven. Very soon, I'm going to show you some types of data. So the first one is supervised machine learning. Works on labeled data. Write down labeled data. Take note of labeled data. Labeled data to make predictions or to make classifications. Now, when we say labeled data means that it has a target variable that it works on. I'm still going to come back to that later on. But let me quickly tell you that the second type of machine learning is what is called unsupervised machine learning, which means that it is the opposite. It has no target variable. You are not predicting anything here. You are only trying to detect patterns. You are only trying to cluster data. You are only trying to maybe do some kind of dimensionality reduction. Maybe you have 1,000 variables. You want to reduce them, not predicting them. right? You are reducing their dimensions, or you are grouping them, or you are clustering them. That's when we say we are doing unsupervised learning. Please pay attention. I'm going to ask you questions, especially those of you that don't have any knowledge before about it. Now, there's a third one, there's a fourth one, there's even a fifth one, but these two are the most popular. These two are the most popular. Take note, these two, supervised machine learning and what? Unsupervised machine learning, are the most popular types of machine learning. But there's a third one called reinforcement learning, which makes use of agents, where agents make decisions by trial and error, and in order to make decisions, and then there is reward. They follow a particular policy. That agent follows a particular policy rule to traverse the environment, not to make to get reward or punishment. This is the type of learning or algorithm that is being used in games, for instance. You see, sometimes when you're playing game on your handset, this is the algorithm that was used to develop that game, or even some autonomous car, self-driving cars and all that. For games, for instance, you will see that if you play according to some rules, you win. Otherwise, you get punished, you lose. So that is, and then sometimes it could even be trial by error. You don't have a predefined data. You're just going around, trial by error. So that's just it. Supervised learning, yeah, reinforcement learning. It's not so common among physical scientists, but then we have to be aware of it. There's also semi-supervised learning, semi-supervised learning, which combines label and unlabeled data to make predictions. Now, what is labeled data? Labeled data has the predictor and the predictant. You have Y and X data. Y unlabeled data does not have any Y, no target variable, no predictor, no predictant variable, no response variable. Everything is just predictors, features that are to be classified or reduced. Okay. There's also transfer learning, which uses knowledge from one task to aid another, so on and so forth. We can use knowledge from supervised learning to aid that of unsupervised learning, or vice versa. So these are the types of learning that we have. There's also representation learning and various other types of learning, representation, image representation, and all that. That's going into a little bit of deep learning. I'm going to tell you the difference between deep learning later, where deep learning comes in. Please just pay attention and follow through. Now, there's also self-supervised learning, which generates labels from data itself. So this is also a possibility, a common type of learning. Now, let's go into them one by one, but let's see more illustrations. Now, this is a diagram showing the major types of machine learning. We have supervised learning, don't forget. We have unsupervised learning, don't forget. We have reinforcement learning. Those are the three major types, but even out of these three, these first two are more common. more common. But then mostly these three are mostly discussed. But then and sometimes those other types are just an aftermath of these ones, these three. Now, under each type of learning, you have different algorithms that can be used that have been pre-developed by scientists, by statisticians, like computer scientists, by physicists, by mathematicians that have been discovered, this algorithm. For instance, naive Bayes, classifier, you have decision trees, you have support vector machines, you have random forest, you have k nearest neighbor. There is mathematics that governs each of these models. They are also called models. Let me tell you, algorithms in machine learning, they are also referred to as models. We use model and algorithm interchangeably, right? We use them interchangeably. So it's either you say naive Bayes model, classifier model, or classifier algorithm, decision tree algorithm, or decision tree model. So now, what differentiates under supervised learning? You know, supervised learning is the one that has label data. Don't forget label data. What even differentiates all of these types of algorithms or models or learning? It is the type of data, don't forget where I started from. It is the type of data that they use. And we are coming to you as medical doctors because you generate a lot of data. And so you see that all these type of learning are very, very useful in your field. They are useful in statistics, they are useful in finance, they are useful in any field you might be, right? So now, look at it closely. I said supervised learning contains label data. Looking of label data, you have a data that really has a target variable that is labeled. The target variable is labeled as yes or no. For instance, you may want to predict why people will not attend lecture today. What are the predictors? What are the possible predictors of why people will not attend lecture today or why people might attend the clinic more today? What are the possible predictors or explanatory variables? Number one, it could be that the accessibility to road to transportation. Number two, it could be accessibility to funding. Number three, it could be their income. Number four, it could be government policy, and so on and so forth. We're already counting predictors that can be used to predict the target variable, the label data, whether somebody attend, yes, you label him yes. Whether somebody will attend, not attend, label him no, yes or no. That's categorical response variable or target. We call it target variable or response variable. Why? So now if you are predicting something with some other variables, like I've described, the one you are predicting can either be categorical or it can be continuous. It may not be categorical. It may be income, for instance. So you might want to predict what is the income, what is the income of a group of doctors. You might want to predict their income, maybe a group of doctors or professors. What is their income? level. You want to predict it. Income is not categorical. Income is continuous variable. It is quantitative variable. It's not qualitative variable. It's not a categorical yes or no or high or low something. It is a quantitative variable. So when what is on the right hand side is that is what is on the right hand side. That is why when it is categorical, then we're talking of classification. We're talking of classification. When the model you are working on uses a categorical data, please write it down. Use a categorical data as its response or target variable, then that is classification. But when the model you are working on uses a continuous data or quantitative data as its target or response or dependent variable, we are talking of regression still under supervised learning. So that's just what differentiates them, is the nature of the target variable. And when you have that situation, these are the types of algorithms you can use for such. When you have categorical variable, yes or no, survive or not survive, things like that. These are the type of algorithms you can use that are made for classification. If you use them, some of them on regression, on a continuous outcome, it won't work. But some of them can do the two. In fact, most of them can do the two. They can do both classification and regression. You can use them for both. Is that okay? So I hope you got the difference between classification and regression. It's going to be one of the questions I'm going to ask you. Now, on this other side, remember I told you the aim here is not to predict anything. It works on unlabeled data. It's just probably to cluster a group of variables or to group them, right? So we have the following algorithms. It's either to find the association between them or to group them or to reduce their dimensions. So this is what it does. So we have the following unsupervised algorithms. We have k-means clustering, k-means algorithm. We call it k-means algorithm for clustering. We have what we also call mean shift clustering, which is similar to k-means. We have the density-based algorithm with noise for clustering. That's db-scan. And we have agglomerative hierarchical clustering. We have a Gaussian mixture model algorithm for clustering. So these are powerful algorithms that can be used. And if you can imagine, if you have a data set, medical data set, by the time we get to the research aspects, any of these algorithms can be used. Maybe they have not been used on that particular data before. It can be tried. Once you know how to do it in Python and you know how to try it, we have codes, we have methods for doing all of this. And that's the essence of this course. You can just try to use any of these algorithms for your data and also maybe probably publish with them, right? And they can be applied to any field, right? And we have also reinforcement learning. We have the Q learning, R learning, TD learning, and all that. So we have various types of algorithms. These are just some of the most popular. There are so many types. So now let's break it down more and let's try to revise again. I told you that supervised machine learning is a kind of learning where an algorithm learns to make predictions or classifications by training on the label data set. Now, there's something that characterizes supervised learning. It has to split the data into two. Please write it down. Supervised learning, in all the learning you have been doing, if you have ever done any analysis before, statistical analysis, you don't have to first split any data you are working on into two. But here, you have to split it into two when you're predicting something in machine learning. And that's what even makes it machine learning. That's one, because supervised learning is like a majority part of machine learning. You have to just split the data into two. You call one the training set, you call the other one the test set, right? So the algorithm will first learn on the training set for it to now evaluate with the test set. So, of course, you know that you have, like I've told you, the data will contain both input, what we call input and output data. We have the dependent variable, in statistical modeling, we call it dependent variable and explanatory variables. But here we call it target variable and feature variables, right? Feature variables, which target variable is the output data, which is labeled as either yes or no sometimes, or it could be values. Okay, now the primary objective of this type of learning is to map the output. Don't forget, I've said it again and again. Don't forget to map a particular predictant with some set of predictors or explanatory variables, right? And it will then allow it to make some kind of accurate predictions or classifications on new, unseen data. Now, I'm going to tell you how. Let's look at some of the key characteristics. I've said it, label data. Don't forget, label data which will be used for training. And then we have prediction or classification. Don't forget, when the output data, the reference target data is categorical, we call it classification. Otherwise, we call it regression. Is that okay? Now, there's feedback mechanism where the algorithm receives feedback on its predictions. That's what I said before. Then you have to now iterate it again. If the the output or the result it gives is not good, you have to try again and again. There's a lot of trial and error in machine learning. And so you have to learn to adjust some internal parameters. So we call it hyperparameters. And then you improve the performance of the model. That's just what we do in machine learning. It's not as if you are the one that developed the model. No one develops new model in machine learning. But what you do is to sit down with the model and keep adjusting hyperparameters in Python or R. Those things are already there. That's what we do, right? And that's what we are going to train you to do. Now, I've told you some popular algorithms that are already there that have made. We have linear regression, even logistic regression. These were borrowed from statistics into machine learning. But one major difference, the way you use it in statistics and the way you use it here, that you have to separate it into two. You have to divide the data into two aspects, two parts, training and what? Test set. We're going to see all of these. All this will make more sense by the time we start the practical aspects, even though you have not done it before. We have taught people in time past and they caught up easily, and they themselves, they started even teaching. You can see some of our past tutors, even here, they've been students here before, and they are now really teaching, and I'm sure you too will start teaching very soon. So you see, support vector machine, decision trees, random forest, naive Bayes, KNN. Now the choice of the algorithm depends on the problem you are trying to solve. And I've said that before. The nature of your data, don't forget, is highly data-driven. Highly data-driven. So don't say, oh, why did this person use KNN and I'm using naive Bayes? We have to see what type of data do you have. Why is he using logistic regression and I'm using linear regression? You have to see the type of data you have. Linear regression is mainly useful for predicting continuous outcome or discrete outcomes. But logistic regression is used for predicting categorical outcomes. We are going to do that next week. We're going to see it. Dr. Fumi will teach you that next week. We'll see it in medical applications. Now, supervised learning is just a fundamental approach in machine learning, and is very powerful. It forms the basis for many real-world applications. Why is it called supervised learning? You can supervise it. You can, if you adjust the features, the predictors, it can affect what is being predicted. Take, for instance, you are working in a lab. You want to mix some chemicals together. You want to see whether it will turn that chemical, the final output will turn green or yellow, or it will turn sour or neutral. It depends. You can decide to add so many features, so many other chemicals, different chemicals. You can adjust the mixtures that you are putting into it. You can supervise it. You can adjust the texture, or you adjust the concentration of each of those mixtures you are putting into it to bring out the final output, and you can supervise it. So that's what really is very similar to what obtains here, supervised learning. So you supervise some predictors, people, those that are predicting the output. If you arrange them, depends on what you do to them. If you add to them, if you do anything to them, they will tell you, it will affect the final output, what is being predicted. So it's supervised learning. It has to do with Y and X mapping, using something to predict something, right? That's why it's called super. And most cases, in most areas of life, we always try to predict. We always try to predict. There's no hardly anywhere where we don't try to predict. That's why I said supervised learning has taken the center stage, even in machine learning, even in artificial intelligence. So it is the most popular aspect of machine learning, right? So let's rush. So what's the difference? you might have known from all I've said. This one, please take a look at this table I created. This one has output, that's response. And the other one does not have any output label, it's unknown. There's just some kind of scattered features that needs to be grouped. So this supervised learning is a predictive modeling technique for predicting future outcomes accurately. But this one is just a kind of descriptive technique. Descriptive. It's descriptive in nature for explaining some grouping relationships. Now, this includes classification and regression, like I said. Here you will see things like clustering and association or between the variables. Well, can be more accurate because of the predictive nature, and the grouping here may be less accurate. This requires splitting the data. We call it data partition. Write it down. That's a key word in machine learning, data partition. Here does not require any data partition. This uses sensitivity, specificity, accuracy, ROC coils, and all that for judging the model. They call it metrics of the algorithm. But here we have purity score, entropy, and all that for internal and external validation of the result. Now, we have so many algorithms here, while we have less algorithms here. Okay, now here is a diagram talking about them in more pictorial form. Look at them. I told you these are the two major popular types of learning in machine learning, right? This is further divided into classification and regression. By now, you know the difference. And this uses unlabeled data. This is divided into different types of methodology, clustering, association, and dimensionality reduction, right? And you can see it clearly here. Okay, let's look at semi-supervised learning. It combines both, like I said before. For instance, a model is trained on a data set that contains a mixture of labeled and unlabeled data. And this approach is very useful, is popularly or particularly useful when obtaining labeled data is quite expensive. So you can try to convert some unlabeled data to labeled data. Okay, these are the characteristics. It has both labeled and unlabeled data. It combines both of them, and then it makes use of transductive and inductive learning, where you make predictions specifically for the unlabeled data in the data set, or you generalize the model for new unseen data, which is known as inductive learning. Now, it has a lot of applications. You know, we can classify text. There's a lot of research you can do. I can analyze your text for you. I can analyze patient reports for you. If you have some patient report, if you arrange it, I can throw it into this algorithm. It will plot it. It will analyze it. That's we call it text classification. Also image too. We can analyze image. We can predict image. We can classify image. Rather, image recognition. We have recommendation systems. For instance, where if you are online, maybe you want to buy some medical equipment, You buy one, you buy pipette, for instance, it will already recommend burette for you. These are the kind of algorithm that have been used to develop such. Or you buy raincoat, it will already recommend boot for you. You will see it online. It will come up. What happened is that that site has been studied, that have been divided into training and test set, that have been the data there has been trained, and then to be able to identify newly unseen data, and then you can easily predict or recommend what will come up next. Another one is anomaly detection, where we try to identify rare events in a data set. Another name for anomaly is just outlier. So some of these models can detect outliers easily. So semi-supervised learning is a very practical approach for many types of application where obtaining label data could be challenging or costly. Now let's go into some other methods. Ensemble methods. There's something called ensemble learning. What is an ensemble? Ensemble models are models that combines predictions from several models in order to make the best prediction. So they are more powerful than the usual individual models. So when you combine, there's a way we can do this also in R or Python, and combine models together or predictions from models together to get the best prediction, right? So this is done in order to achieve overall best predictive performance by aggregating predictions of multiple models in order to enhance robustness or increase accuracy of the model. And it's usually effective when individual models have different weaknesses or even strengths. Also, we have base models. Don't forget, base models and the individual models, the homogeneous models. And sometimes they could be the same type of model. Let's say several decision trees together. Or sometimes it could be decision tree, support vector machine, EBEs. That's when we have heterogeneous case. And then they can be trained independently on data. Then you match their predictions, or you vote for the best prediction, or you match them, or you average them, and you enjoy diversity. You can bring different models together and get the best from them. And then you can even reduce overfitting. Overfitting is when the model performs best on the training data and does not do much with the test data. We don't want that. We want it to do much on the test data. Okay? Now, common ensemble methods, they are also divided into about 3 or 4. We have bagging, also what is called bootstrap aggregation or aggregating, where it trains multiple instances of the same base model. Remember what I said, it could be the same decision trees on different subsets of data. So it will divide the data into different subsets, different sets, and then it now combines their prediction. And by this, it must have reduced the variance and improve model stability and reduce overfitting. Random forest is one good example of this. Okay, so random forest is a very popular implementation of back. Another one is boosting. Boosting. This one combines several weak learners to get models that perform severally are better than random child in order to create a strong learner. So it does it sequentially. Okay. Now, we have examples like gradient boost. These are very powerful models. XG boost, ADA boost, gradient boosting. I want to write a paper on boosting very soon. I'm on it already. And these are very, very powerful uh, algorithms that could perform, in fact, that are being used in our day-to-day activities. And we're not going into the mathematics yet. So when we do voting ensemble combines the prediction from multiple models and then it will vote for the best. Let's say each model, one model votes that the prediction is 1. Maybe you are trying to predict 1 or 0. Let's say another model predict that it's 0. Another one predict that it's 1. Another one predict that it's 1 again. By the time you are voting, then by the time you apply voting, then it will vote for the 1. Then that means the one with 1. 1 is the prediction, you know. But let's say you are working on continuous data where it's not 1 or 0, it's not categorical. Then what you do is to average them, all the prediction. Maybe one predicts 0.9, another 0.96, another 0.7, like that. Like you average them together and get the final prediction. That's voting. Then stacking is another assemble method where you use a base model to predict a gain. You apply a meta model, another meta model, maybe sometimes usually logistic regression on all those predictions instead of voting or stacking, or averaging. You now throw all those predictions into another model, and then it will produce its own singular data, singular prediction, and then that will be taken as a final prediction. Is that okay? Then there's also blending, which is similar to stacking, but it will divide the data into two parts. Again, that's another even more powerful. It will do training and testing on those predictions again. And then it will now give final prediction. We have written papers on all this. And these are areas you can apply to your medical research that can take you higher. In fact, you can get published in top journals. We're already used to all this linear regression, all these common models. But by the time you begin to go more advanced, stacking, blending, voting, aggregated model, ensemble model, you will see that it will do justice to your data. Now, ensemble methods are widely used machine learning algorithms because they often lead to very significant improvement in predictive performance, and they are good for both classification and regression tasks. And the application is vast. It can apply in medicine, finance, econometrics, various aspects. Versatile technique with versatile applications that enhances model accuracy and robustness. So let's wrap up. What are the key components of supervised machine learning, which we have covered today? Maybe next time we'll cover unsupervised machine learning, we have said it is highly data-driven. That data could be labeled or unlabeled. Then we have models, which is also referred to as algorithms. Then we say that those models vary in terms of use. You can use some for classification, you use some for regression, all other. And we have features. Features are the predictors, the variables in the model. Okay. Then we talk of or when we begin the practical, we begin to talk of how to handle new features, how to transform data to generate new features, undo missing data, and then encoding categorical variables, and so on and so forth. Now, I also talked about label, target variable, label. I talked about training data, which is also always you divide the data into about 70%, 30%, 70-30 divide. You must divide the data into two in supervised learning. One is for training, one is for testing, right? And then the testing data, which is the other 30% or 25%, as the case may be, is used to evaluate the model's performance and to help assess how well the model generalizes to new unseen data. This test data is not in the algorithm at all. It will just be put there, to just be used to evaluate, to be brought in for prediction, whereas it wasn't in the original algorithm. So I said also algorithms are often used. Most of them are called algorithms. They are computational methods to optimize model parameters and learn patterns from the data. And I told you that the choice of algorithm depends on the problem and the type of data. Now, there's something called loss function. This is a bit mathematical, or sometimes we call it cost functions, which quantifies the model's performance before it to be iteratively remodeled. Now, what is, usually a model will predict, it will predict a value. So that value it predicts, you can compare with the true value that is supposed to be. And then you see the error. So that error must be minimized to the barest minimum. So the difference between the predicted value and the actual value is known as cost function, and they can be of various forms. It could be mean square error. It could be root mean square error, especially when you are working on a regression task. It could be mean absolute error, and so on and so forth. The goal is just to minimize its function during training, to minimize this particular function during training, to reduce the gap between the predicted and the actual to the barest minimum. And that's what is being done also in deep learning. I taught a course on deep learning, I think last semester, about 2 months ago. And some of these things are very, very related. They might look very big in names, but they are not really difficult to understand. You just need to pay good attention and concentrate and don't be scared. So you need some optimization techniques to minimize your loss function in order to reduce bias, especially in deep learning. We'll see that you have some weight and uh, and uh, 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 and the constant value. These are the parameters that will be minimized via gradient descent, which is an optimization technique. There are so many other optimization techniques like Adam, like RM, Adam, combinations, hybrid, Adam, and all that are useful for minimizing loss function. All is just to improve model performance. Now, there's what is called validation set. Sometimes we divide the data into three, not two, in order to just fine-tune model hyperparameters. You use the test set to evaluate, then you use validation set to validate. And then this really helps us when we have so many hyperparameters in the model, especially in the decision tree models. We have some hyperparameters like learning rate, depth of the tree, and so on and so forth. And this helps us to assess model performance during the training set. By now, you know hyperparameters. They are parameters that are not inside the algorithm, that they are outside, they are specified outside the algorithm. It's just like, for instance, you want to purchase a car, you want to bring your car. There are other things that are necessary in order to get your car to the venue. Maybe you are importing it. Like what type of vehicle will bring the car, apart from doing the major thing, paying for the car and selecting the real car you want to buy and paying for it. But what kind of port will it go to? Those are other minor things that can help you to get your car faster. Sometimes they may not be necessary. You might just give it to chance and just don't care about it. But if you go ahead and specify, I want this particular port, my car to come from this particular port. I want this particular driver or this particular uh, 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 mm, vendor to be the one. Those are hyperparameters. Sometimes you just give it as something, bring it for me. You don't care of all those minute details. Or I want it to come with this particular size. Things like batch size, learning rate. I want it to travel at so rate. Those things are hyperparameters in model design. But sometimes they help to improve model performance. Sometimes they don't. Sometimes they are not necessary. Sometimes if you specify all that, it's still the same result, right? So those are called hyperparameters. Then there's also what is called cross-validation. Cross-validation is a term used in machine learning to denote a technique to assess model performance. What is being done here is that you divide the data, the original data, to go ahead, apart from the training and testing, to still divide the original data into multiple subsets again. And it will train on different combinations of those multiple sets. And then it will average the results again. That ensures high performance, and this is a method that is very, very useful in machine learning. Sometimes when you divide the data into 10, for instance, that's tenfold cross-validation. That's where the name tenfold cross-validation comes. So they call it, another one method is k-fold cross-validation. When K is 10, then it comes a 10-fold cross-validation. Take note, by the time we give you Python codes and you see K equals 10, you know where it comes from. You know what I'm talking about. So if you specify 20, if you specify 25 or all that, you see whether there will be a difference in your results. These are things we will allow you to practice with. Okay? Now, there's another term known as metrics. Metrics. What are metrics? Metrics are the judges, the numbers, the quantities that are used to judge the models, whether they perform well or not. They are used for judging model performance. Examples are accuracy, sensitivity, specificity, precision, recall. Recall is another name for sensitivity. F1 score, which is the harmonic mean of precision and recall. And then they are used to quantify the model's performance on either classification or regression tasks. Now, these are for classification tasks. When you are doing regression tasks, you can't use precision, accuracy, recall. You use mean square error, you use root mean square error, you use R square, and all that. Okay? We wrote a paper on metrics, on different types of metrics. We have Matthews correlation coefficient. These are new metrics that are being developed. You can also develop your own metric or see which metrics works best for a particular medical data. Okay. And then we have regularization techniques in order to reduce the dimension or to remove redundant variables from a model. They are also used to prevent overfitting. When redundant variables are in a model, they can lead to overfitting. But here, when you apply L1 or L2 norm to regularize the model, it will remove, to serve as a penalty that will turn it will turn it to 0 or 1. It will turn the redundant variables to 0, L1 norm, or it will turn it to 1, L2 norm. Example of these regularization methods are the lasso or the ridge regression. I don't want to go into all that now. We'll get there for those who are interested in more mathematical applications. Okay, then not only that, after you have selected your best model, you have to deploy it. You have to deploy it. After testing, you have to deploy it to make predictions. You can put it at the door of a clinic. We wrote a paper on malaria diagnosis and it was deployed. Another group wrote another one based on that one I wrote, and it was deployed in Kenya. That students, when they go to clinic, for instance, wrote our own algorithm to be able to, they will enter their data and it will tell them whether they have malaria or not. Yes. So these are the types of models. These are things that are possible. You can do that in your own clinic. You can deploy an app. You can, if you really take what we're teaching serious, you can be able to develop your own algorithm, a machine learning algorithm that will be able to diagnose a particular disease, and you deploy it to your clinic or to your government. It's possible. If you are interested, let us know. It's possible. It's human beings like us that did all these things. It's possible. Now, but you have to keep monitoring all those, the algorithm you deploy through feedback mechanisms, and then you continuous testing and then you may have to redesign the machine learning algorithm again and then redeploy again. And so we see it has various tasks, various applications, which is really, really useful in our day-to-day activities. Various applications, image recognition, natural language processing, recommendation system. We have mentioned some of financial services, healthcare, used for disease diagnosis, drug discovery, predictive analytics. We would like to see some of these used in marketing, autonomous vehicle, energy management, agriculture, and so on and so forth. So many applications, sports, education, and so forth. So, but there are challenges. The data quality. That's why we are taking time on data. Data quality, data quantity. How do you address your data? That's why we are doing some Python activities on Python or R, be able to assess your data quality properly. Or quantity. Sometimes you don't have sufficient data, your model will perform poorly. Like that long data, we'll see how it performs. I'm going to forward an algorithm to you. I'm going to forward a code to you after this course. We're going to see how it works. Maybe tomorrow we're going to try to work with all of this. We're going to see it practically. Get ready. Tomorrow we're going to do the Python exercise on all of this. You're going to really see results. Please take note of all these keywords. You're going to see them play out practically. Python, and you're going to see that you can do it by yourself. So these are challenges. Interpretability, it could be challenging to interpret sometime, but then nothing is impossible. There are also, especially when it comes to medical areas, ethical concerns, security, and so on and so forth. Cyber security. Sometimes you deploy your model, it could be susceptible to cyber attacks or data poisoning. Then scalability. After training and deploying, the same model be scaled up to different data sets? That's a challenge, or you have to rebuild the system again, you know. So algorithm selection is also a challenge in machine learning. That's the major task because you're not the one to develop the algorithm, but you are the one to select the best algorithm for your data. That's what we do in machine learning. Okay? So, and that's what you are going to be doing when we start our capstone and research project in this course. Because it can be complex and the optimal choice may vary from one problem to another. Then when you talk of hyperparameter tuning, it's another big challenge you're going to see. And privacy, regulatory compliance, and then sometimes lack of domain knowledge. So if you must use machine learning for a particular data, you must have knowledge of that medical area, for instance. You don't just say this data, apply machine. What do you want to achieve? What do you want to do? And that's what we are going to discuss now. So I'm going to stop the class very soon. Then I'm going to allow you to identify some kind of domain knowledge, domain areas you think we can apply all these methods to. And then we're going to start doing it. Then there could be imbalanced data sets, which is very, very common. Very common. This is the topic I went to teach in Rwanda some few years ago, a few months ago. imbalanced data sets, especially in medical data, is very, very common because, the number of people that have the disease versus the number of people that do not have the disease. Mostly, the number of people that have the disease are smaller, fewer than the number of people that do not have the disease. But do you know that it's the people that have the disease that we're more interested in? So there will be data imbalance. So you can't treat them the same way. You have to balance, you have to find a way of balancing the data. The number of people, mostly except if there's an epidemic, number of people that will survive be more than number of people that do not survive. And you're trying to predict the number of people that will not survive. So you need to find a way of balancing the data. The data will be highly skewed, be highly imbalanced. So we'll use techniques like cost sampling, like applying adaptive synthetic data generation to help mitigate this data imbalance. We have smooth method like uh, smooth addressing, hybrid methods, and so on and so forth. Very rich method. That's another area of research. And could be also dynamic environment, you know. Machine learning might not adapt well to dynamic evolving data requiring continuous model updates. You have to keep updating your model. Then here's another big one, explainability. In some applications like healthcare and finance, the ability to explain the model, what the model predicts, is very, very crucial for gaining trust and regulatory compliance. You need to be able to explain. In the past, machine learning models were not explained, but now there are different methods for explaining models. This is another great area of research. We wrote some papers on this area recently also, which is very important for the audience, I mean the general populace. And this is one aspect I really like in health data science. Okay. Transfer learning could also be a challenge where it can be challenging to fine-tune pre-trained models for specific tasks effectively. It's not easy to transfer the learning like that. Then we have other methods like other challenges like testing and evaluation and so on and so forth. But you must understand that for you to address this challenge, you need a combination of data reprocessing, model selection, several evaluation strategies, trial by error, and you must, in all of this, you must still adhere to ethical and regulatory guidelines. You are not allowed to go follow the shortcut. That's where machine learning is hard. It's very powerful, very useful, but it could be time consuming. It could be tasking and time consuming and tiring, but you must not give up. Okay, we must really, as researchers, we must be ready to develop solutions and tackle these challenges to have harness the full potential of machine. And that's why we're having this course. Let's see how we can apply machine learning to practical areas like health data science or medical data and see what we can do. Now, there are tools that are useful. You must have known we have started on Python, NumPy, Pandas. Scikit-learn is the major library for machine learning. we're going to look at it. Matplotlib and Seaborn, they are for plotting, visualization. NumPy, Pandas, they are just fundamental or essential tools for numerical data operations and data manipulation. And your Jupyter Notebook is what we use here. Jupyter Notebook, please get your Jupyter Notebook ready. It's a very great IDE, interactive environment for data exploration and analysis. I'm going to share some more notebooks with you. So for deep learning, we have TensorFlow and or Keras or PyTorch. So for we have libraries like XGBoost also for assemble methods that I talked about for structured data. So in R, we have Caret. Caret is very powerful. I love Caret. We have ggplot. Caret is used for machine learning. It's called classification and regression trees. Classification and regression trees is very powerful. It's a unified interface for various algorithms. ggplot, powerful library for data visualization and plots. Random forest library is also there for assemble learning. E1071 is also good for various types of machine learning, support vector, and all that. We also have Keras and TensorFlow in R also for deep learning. Okay, we have other languages that can also do it, like Java, Scala, C++, C++, and all that. And also several data processing tools. That is what is called auto machine learning, is to just do all this automatically. You just do it automatically. But this does not allow us to learn so much. Things are getting easier and easier. If you put your data in auto ML, it will select the best machine learning model automatically and then give you your results immediately. But then we'll not go into that. Deep learning is also an interesting part. We'll talk about it later. And now we like to give room for questions. We have discussed all of this. I would like to give room for questions. By the time I share this slide with you, it's just telling you clearly again the differences between classification and regression. You will see it clearly and you'll see this summary. I've talked about k-fold cross-validation techniques. And then the no free lunch theorem in machine learning is a very powerful theorem that is attributed to a guy called David Wolpert that says that there is no universal or one-size algorithm that fits all data and that performs best for every possible problem or disaster. You have to keep trying. One algorithm may perform well for this data, it may not perform well for another data. So that's why you have to keep working at it until you get the best algorithm for your own data set. Is that okay? An algorithm may excel in one type of problem and may not excel in another. So the effectiveness of an algorithm is highly dependent on the nature and structure of the data it is applied to. So we'll see more of it by the time we start doing the practicals tomorrow. So in conclusion, supervised machine learning is a building block of a transformative field called machine learning. And this field has reshaped many industries, many hospitals, several applications in the world. And this particular machine learning field is grounded in data analysis and statistical principles that empowers machines, computers to learn from data without being explicitly programmed, like I've said before. So the demand for machine learning continues to rise. So welcome. This is the time for you to key into it, begin to learn and begin to adapt to it. And you need continuous learning and adaptability. Whether you're a beginner or experienced practitioner, the pursuit of machine learning knowledge is going to be rewarding, and it will offer you a range of opportunities for innovation and impact. So I want to thank you for listening, and I wish you the best in your pursuit of knowledge. I'll give room for questions now. Thank you.
Thank you very much, Prof. That was really very, very wonderful. Actually, I've learned a lot. But there's something I want to ask. We are talking about algorithms, also being known as models. Now, I want to see, for instance, if you have an algorithm, so I want to believe that an algorithm is like sort of a code that you have written to solve a particular problem. I don't know, am I right to say that, Prof?
Yes, yes.
Okay, so that means, for instance, all these already existing algorithms, they're already in R. You can tweak any of them to suit your purpose. Can that be done? Hello, Prof, do you understand me?
Yeah, you cannot really tweak them, but you can tweak their parameters and hyperparameters.
Okay. Why I'm asking, assuming I want to do a prediction on heart disease now. I get, and I want something innovative. Is it still the algorithm that is already existing that I'm going to use to run it, or I'm going to come up with, but I don't know, just explain to me, assuming I want to develop an algorithm using optimization for prediction of heart disease. How do I go about it?
Yes, you can join two algorithms together. For instance, you can develop hybrid algorithms. But in machine learning, it's very difficult to tweak an existing algorithm to achieve a purpose. Yeah, but you can. I'm going to share more insights with you by the time we start the practicals. I'm going to share some papers with you where we have really tried to do some new things. And there are some times we'll submit papers and they say there's nothing new in this. It's just running some data on this algorithm. Now, they will now suggest some things to do. Why don't you do more, go deeper, maybe try to tune the upper parameters or try to combine some algorithms. And may I tell you that even most of these algorithms that they are telling us to do, they are already existing as libraries in Python or R. In fact, if I show you Caret, I thought I showed you Caret before, one of my past webinars with you. Maybe we didn't have time to do that when you invited me at Uniport. We can see that there are about 300 or is it up to 400 models already existing in current that people have developed. So, but it's possible for you to try something, but it may take longer time. It's possible. But there are other ways you can try to combine things that it will still look new, especially for your heart data. When we get there, we'll talk more about it.
Okay,
Is that
Prof.
okay?
Thank you. Yeah.
Yeah. Mm.
Yeah, Prof, thank you very much for the lecture. In fact, it's really loaded. It's unfortunate that I've been struggling with the network. I joined very late, but I think I have to go through this again and again because I think this is now I started my own lecture, my own lecture. Thank you very much, sir.
You're welcome. Sir. Thank you. More